Today we're going to talk about section 5.5, which is on solving polynomial equations. We're actually going to break section 5.5 into two parts. Part 1, day 1, we're just specifically going to talk about factoring perfect squares, and then also a new one today, factoring perfect cubes. Okay, but we're just going to concentrate on the factoring part of it today. And then in day 2, tomorrow, we'll concentrate on the solving of these polynomial equations. But first of all, let's talk about factoring. Now, we've done some things with perfect squares before in the past, and we factored some perfect squares. And for example, we've taken a look at something like this, a difference of perfect squares. Okay, and we came up with this little rule, or this little pattern with these perfect squares a while back, where if I have a difference of perfect squares, the first number is a perfect square, the second one's a perfect square, and they're separated by subtraction, it can be broken apart into these two little expressions, but it had to be separated by subtraction. Well, if I look closely at this, am I able to factor this? Are they perfect squares? Well, yeah. X squared is a perfect square. And how do I know what goes in this first parenthesis? When I went from here to here, we took the square root of that number. Okay? The square root of x squared was x and x. Is 9 a perfect square? Yep. The second number, what went in the second spot was the square root of that number. 3 and 3. And if you look closely, one of the signs was plus and one is minus. And again, the sign, the operation doesn't matter. They can be in either order. But my point here is that we did the square root of each one. Okay, when we broke it apart into its different pieces. And again, we're concentrating specifically on the factoring. Okay. Here's another one. What if I had 16x squared minus 25? What if I had a number that went out in front? Okay, out there with it. Well, ask yourself, is 16 a perfect square? Does it have a nice square root? It sure does. The square root of 16 is 4. And I have to put an x and an x. 25 is a perfect square. The square root of 25 is 5. So a 5 and a 5. And one is plus and one is minus. And notice again, why the opposite signs? Because when you FOIL, the middle terms go away. Okay? But there's one. There's another one. Okay? How about another one here? Got a couple others. Just refreshing our memory with perfect squares. Okay? What if I had one that was, maybe something like this. 64a to the 4th minus 9b to the 4th. Can fourth powers, how about that? Can fourth powers be perfect squares? They sure can. Okay? I'll get to that in just a second, but if I look at my numbers, 64 is a perfect square. The square root of 64 is 8. So 8 and 8. 9 is a perfect square. It's going to be 3 and 3. But what about that a to the 4th? How about the square root of a to the 4th? The square root of a to the 4th is going to be a squared and a squared. And if I FOIL it, if I was to FOIL, do I get 64a to the 4th? Yeah. And what I did there is I just divided the exponent by 2. Okay? Same thing with b. The square root of b to the 4th is b squared and b squared. One is plus, one is minus. And one thing we always have to check for, especially when we start out with a bigger power than a squared, is once I factor it, can either one of those be factored any further? Okay, now there's only two terms, so I'm thinking, is it going to use this little pattern? Okay, but I can't use it because 8's not a perfect square and 3's not a perfect square, so we're done. And I can't do it on this one at all because it has addition in it. Okay, but yeah, we can have numbers in front. We can have powers bigger than 2. Let's try one more of these x to the 4th power ones. Okay, how about this one? 36 x to the 4th minus 49 y to the 4th. Okay? Do we have perfect squares? I'm liking the numbers 36 and 49. The square root of 36 is 6. And the square root of x to the 4th is x squared and x squared. X to the 4th are almost always going to go to x squared and x squared. 49 is a perfect square, 7 and 7. And I get y squared and y squared. One is plus and one is minus. And once again, can I go any further, especially with the minus one? Nope, 6 isn't a perfect square, neither is 7, and we're done. And we can't do anything with addition. Okay? So again, that's a quick review of this little pattern, factoring perfect squares, with the addition of maybe adding a bigger power. Okay? But again, if I had x to the 6th, okay, then I divide it by 2, it would be an x cubed and x cubed. If it was x to the 8th, y to the 8th, it'd be x to the 4th and y to the 4th. Okay, we're just going to divide those exponents by 2. Okay? All right, I have one other one here for us before we move on. Okay, and what if I had this? 27 x squared minus 125. Okay, now I'm thinking, there's only 2 terms, but bad news. 27 and 125 are not perfect squares. They don't have nice square roots. So now what do we do? Okay, well, we took a look at this a while back when we did factoring. Can we take something out? Do they have a greatest common factor? And if you look at your factor sheet and go down 27 and 125, you'll see the biggest number that goes into both of them is a 3. So I'm going to divide out a 3. And watch what happens when I divide out a 3. 27 divided by 3 is 9. And 125 divided by 3 is 25. Okay? And now let's look at what I have left over here. 9x squared minus 25. Can that go one step further? I think 9's a perfect square. 25's a perfect square. I think we can factor this one more time. If I use this little pattern here, I get a 3x and a 3x. The square root of 25 is 5 and 5. 1 is plus, 1 is minus. And there we go. Okay, and oftentimes I get the question, what about this guy out in front out here? He just comes along for the ride. So I actually have 1, 2, 3 parts to my answer. Okay? But this is a biggie. If they're not perfect squares to start with, try to find a greatest common factor, something that divides into it. And oftentimes, after we divide that out, the numbers we have left over are perfect squares. Okay? But that's factoring perfect squares. I'm going to see a lot of them with this little pattern to it. But again, the key is there's 2 terms, and they're being separated by subtraction. Okay? All right, next up is perfect cubes. And this is something new. I don't think you guys have seen perfect cubes before. This page is in your book. Okay? But I'm going to write it over here on the other side, or on the side over here, so I have it as a reference. Perfect cubes. Okay? What if I had a cubed plus b cubed? Okay, there's a little pattern to these as well. Okay? And what we do to get the first number, or to get the first, let me back up. There's a little piece and a big piece. Okay? To find the little piece here, what we do is we do the cube root of each of these. So the cube root of a cubed is an a. The cube root of b cubed is b, and I keep the same sign. Okay? And then what I do is I use this little part to get the second part, the longer part. And what I do, how do I get where this first number comes from? It comes from the square of the first one. So a squared is a squared. I change the sign, it turns to a minus, and then I multiply the 2 together, a times b. And then I square the second number, b squared. Okay, and it sounds confusing, it sounds a little intimidating, but the more you use it, the easier it becomes. And there's also one for subtraction, a cubed minus b cubed. Again, it's the same exact thing. I take the cube root of the first number, the cube root of the second number, and I keep the same sign. So again, we're going cube roots. Okay? Then I square the first number as a squared, change the sign, multiply the 2, and square the last number. Okay? And that's how we factor perfect cubes. Okay? And I'm going to write it over here one more time. Okay? The way that I get these numbers is I take the cube root of each of them. The sign stays the same. Okay? And then this says I square the first number, a squared, change the sign, multiply the 2, and square the second one. And the same is true for subtraction. And this will get a little bit easier once we use it and do it a couple times. But one other thing I'm going to write down here before we start. I'm going to write down a few of the common perfect cubes that we're going to see quite often. I'm going to make a little list, and I think it'd be a really good idea to jot these down. 1 cubed is 1. Is 1 a perfect cube? Yeah. The cube root of 1 is 1. Okay. 2 cubed is 8. The cube root of 8 is 2. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. And 7 cubed is 343. Those are the common perfect cubes that we're going to see. And again, once again, writing them down I think is going to be extremely helpful. Okay. Another good thing that can be helpful is once upon a time I gave you this sheet on a little half a piece of paper a while back that had perfect cubes and perfect fourths and perfect fifths. We would just go down the column that has the perfect cubes on it. Okay. But lastly here, once again, that is in your book. Okay. If you certainly want to look at it, you certainly can. Okay. A couple other things about perfect cubes. Okay, is that when we factor it into the two different pieces here, the second part, the big part, is never factorable. Okay, this part right here is not factorable. That's the end of the road. You can never do anything more with that. And more oftentimes than not, the same is going to be true with that piece. But especially the second part, that's a dead end. Okay? All right, let's try a couple of these ones. Okay? Let's start with a nice one here. How about x cubed minus 27? Can we factor it into its two different pieces? Okay, and I first of all need to recognize them. Well, yep, they're perfect cubes. X cubed is a perfect cube, and I'm going to be using the bottom one here, the subtraction one. Well, how do I get this first number? Well, I do the cube root of it. The cube root of x cubed is x. 27 is a perfect cube. I'm going to do the cube root of 27. The cube root of 27 is 3. And I'm going to keep the same sign. Okay? Once I get this first parenthesis, once I'm done with this one, I'm pretty much done with that. I'm going to use this to get the big piece. Okay? What I do first is I square the first number. It's x squared. I change the sign, plus. Then I multiply the two together. 3 times x is 3x. And I square the last number. Negative 3 squared, it's always going to be a positive number, and it's positive 9. And there we have it. There's our little piece and our big piece. Okay, but I'm hoping you see how we use the little piece to make the big piece. Okay, let's try another one of these ones. Okay, they get easier as we practice them. Okay, how about this one? 125 x cubed minus, let's do plus 64. Okay, I only see two terms, so I'm going to ask myself, are they perfect cubes? Is 125 a perfect cube? Yep. And is 64 a perfect cube? Yes. So to find, I can factor it. To find the first part, I'm going to cube root 125, which is a 5x. And I'm going to cube root 64, which is 4, and I keep the sign. So I just did the cube root of each one. And then I'm essentially done with this. Okay? The first number comes from the square of the first number there. That's 25x squared. Change the sign. Multiply the two together. 5 times 4 is 20x. And then square the last number, plus 16. Okay? So hope it's getting a little bit easier anyway. Okay? I'm going to have you try one more. I want you to try this one by yourself once. Okay? Let's do 27x cubed minus 343 y cubed. Okay? Can you break that apart into its little part, its little piece, and its big piece? So push pause if you want. Give it a shot and then unpause when you're done, and we'll take a look. Ready, set, go. Okay, welcome back. Let's try it. If I was to do the cube root of 27, the cube root of 27 is 3, and it'd be a 3x. The cube root of 343 is 7. And I'm going to keep the same sign, subtraction. So 3x minus 7 is that first part. And then we're done with this. Okay? I square this one to get the first number. So 3 squared is 9x squared, not 6, but 9x squared. Change the sign and multiply. 3 times 7 is 21x. And I square the last number, I get 49. Okay? once again, this leftover stuff right here is never factorable. That's as far as we can go. Okay? All right, very nice. Good job. Okay? All right, I got one more for you here. It's kind of a special one. Okay? And it looks something like this. 64x to the 6th minus y to the 6th. Well, I only see two terms there, and now I see an x to the 6th power. Okay? And I'm going to go back to the top here. Is x to the 6th a perfect square? I always start with those. And it is. Okay? Is 64 a perfect square? It is also. And is y to the 6th a perfect square? Yeah, so these are, what I have stared at me here is these are perfect squares. Okay, let's do what we did at the beginning here. Can I break them apart into just two terms? By doing the square root of each one. This is 8x cubed minus y cubed if I did the square root of each one. And this is 8x cubed plus y cubed. I'm doing the square root. One is plus, one is minus. Okay? Well, look at what we have left over now. I see some x cubes and y cubes. So I'm thinking, hey, maybe these. And I also see the number 8. Is 8 a perfect cube? Yes. So actually, each one of these two leftover pieces, and this is kind of the big new thing that we're going to see the next day or two, is once I factor it once, we're going to be able to continue factoring a little bit more. Okay? Now, so I can do with this one, I can make into a little part and a big part. And I'm going to do perfect cubes. So I'm going to do the cube root of 8, which is 2x, and the cube root of y cubed is y. And I'm going to use my pattern over here. I'm going to square the first one, 4x squared, change the sign and multiply, and y squared. And I can do the same thing with this one over here, a little part and a big part. The cube root of 8 is 2x, and the cube root of y is y. I square it to get 4x squared, change the sign and multiply, and then add y squared at the very end. Okay? So wow, that one actually broke apart into 4 different parts. Okay? That's a tricky one, so be careful, be cautious of that. But I always look for perfect squares first, and then break it down. Okay? All right, I do have a couple special ones here, though. And we saw these special ones with perfect squares. Let's look at this. Okay? So I immediately say I see two terms, but neither one of them, 5 isn't a perfect square, neither is 320. Okay? And I look at perfect cubes. Okay? 320 and 5 aren't perfect cubes either, so now what do? Well, I think we saw this earlier when we did perfect squares. Can we take out a greatest common factor? And if you look closely, I think 5 goes into both of those. And I think I can take out a y out of each one as well. And if I take out a 5 and a y, I think I'm left with y cubed. Oops. And this is going to be minus 64 z cubed. If you did 320 divided by 5, it'd be 64. What about that leftover stuff now? I see y cubed, so I'm thinking perfect cube. And is 64 a perfect cube? I think it's going to work. I think this is perfect cubes. So I can break it apart into my little piece and my big piece. The cube root of the first number is y. The cube root of the second number is 4z. And I keep the sign. Okay? And then once again, I'm essentially done with this. Because I'm going to use the little piece to make the big piece. And what I do is I square the first number, change the sign, multiply the two together, 4yz, and then square the last number. And again, it's 16z squared, not 8, but 16z squared. And then the 5 here just drops down and comes along for the ride. So this one has 1, 2, 3 parts to the answer. Okay, so taking out a greatest common factor and then examining the leftover stuff. We're going to see that more often than not today anyway, that the leftover stuff you will be able to factor one more time. Okay? How about this one right here? 54 is not a perfect square cube. 250 isn't a perfect square cube either. So my guess is they have a greatest common factor. Okay? And, oh boy, that's a tough one. But just for time's sake here, what I'm going to tell you that 2 goes into both of them. And the other thing here is look at this negative sign. Do we like the first term to be negative? No. So I'm going to take out a negative 2. And I think they each have a W as well. And if I take out a negative 2W, 54 divided by 2 is going to be 27W cubed. That's going to turn to plus when I divide out the negative. And 250 divided by 2 is 125Z cubed. Okay, and I'm kind of liking what I see here. Because I think that leftover stuff, I think they're perfect cubes again. 27's a perfect cube, 125's a perfect cube. And so I can continue to factor that into its little piece and its big piece. The cube root of 27 is 3W. The cube root of 125 is 5 with a Z, and I keep the same sign. Okay? And once I get the short piece, the little piece of that, I'm done with this. And I'm going to use this to get the second part. So I square this again, 9W squared. Change the sign and multiply. That's 15WZ. This again. And then I square the last number, 25Z squared. Okay? And the negative 2W comes along for the ride. So again, 1, 2, 3 parts. And like I said earlier, the nice thing about perfect cubes, you can't go any further with the big piece. That's as far as you can go. Okay? All right, I got one other special one. So again, what's been special about these is that they've had a greatest common factor. Okay? See if you can take a minute and try this one by yourself. Push pause, give it a whirl, then unpause. Okay, welcome back. Let's try this. Okay, these are not perfect squares or perfect cubes, but I think they have a greatest common factor. And I think if you look closely, they both have a 3x squared that goes into both of them. 24 divided by 3 is 8, and I get 3 left over. 3 divided by 3 is 1. I think the only thing left over here is y cubed. And this stuff, lo and behold again, they are perfect cubes. We're seeing a lot of the repeat numbers, repeat expressions. Okay, but the cube root of 8, if I did my cube root pattern, I'm going to use the top one here. The cube root of 8 is 2x plus y. Okay, I'm done with this. I'm going to square that to get 4x squared. Change the sign, multiply them together as 2xy, and square the last term to get y squared. And that guy comes along for the ride. 1, 2, 3 parts to my answer again. Okay? So hoping the more you practice these, the easier they're going to be. Okay? But once I say it to yourself, talk yourself through it in using this little pattern. Okay? All right. Okay, one last thing here to talk about today, and we've actually done this before. A little refresher on grouping. Okay, and grouping, how do you know when grouping is used? It's when there are 4 terms in the expression. Okay, and when I do grouping, what I do is I group the first 2 numbers together and the last 2 numbers together. Okay, and notice how I left the plus sign in between them. Okay, but when I do grouping, and there's a little bit of work to show here, once in the first group, in the first set of parentheses, I look for greatest common factors. There's something that those 2 terms have in common. Well, they have an x squared in common, so I'm going to factor it out. When I take an x squared out of the first group, I get x plus 5 left over. I'm going to do the same thing in the second group. Is there something that this group has in common? They have a 2 in common, yeah. So I'm going to take out a 2, and I get x plus 5. Okay? And with grouping, here's the whole key to grouping, is they now have a little expression in common. Okay, they both have an x plus 5, so I'm going to factor that out. It's kind of 2 greatest common factor things. When I take that out and that out, you can see what I have left over is x squared plus 2. Okay, and when we did grouping before, that was the end of the line. But what we're going to want to check for today is we're going to want to check for is does the leftover stuff, can it be factored any further? Are they perfect squares or perfect cubes? In this case, x squared is a perfect square, but that's not. So that's the end of the row. But grouping, 4 terms, we do the 2 groups, factor out the greatest common factor a couple different times. Okay? All right, here's another one. Okay, I see 1, 2, 3, 4 terms. Now this one is special. I don't know if you remember this or not, but I'm going to group the first 2 numbers together and the last 2 numbers. And once upon a time when we talked about grouping, and when there was a subtraction sign in front of the second group, we had to change the sign on the last number. Okay, if it was a minus, it becomes plus. If it was plus, it becomes minus. This one stays the same though, but we have to change the last one. Okay, and then we do the same thing. Does that first bunch have anything in common? Well, I think they have just an A. And if I take out an A, okay, I think I get A plus 3y left over. Okay, and I see my minus sign. Then I look at the second group. Do they have anything in common that I can take out? Well, I think that second bunch here, they both have a 2 in common, and they both have a y squared. If I take out 2y squared, I think I get A plus 3y. You know, one thing you can do to catch yourself, if you forget to switch the sign here, you can kind of catch it here, because if you remember, with grouping, they have to have that little common expression in common, A plus 3y. And if you forget to change it up here, you're going to get the wrong sign. They have to match. But when they're the same, I can take out an A plus 3y. And what's left over? A minus 2y squared. Okay? And that's the end of the road with that one, because they're not perfect squares. Okay? All right, here's the very last one for the day here. Okay? And this one's in your book. And it's a special one. I just put it in here so we don't have to do it, we can just kind of watch it. But holy mackerel, looked like instead of 4 terms, there's 6. 1, 2, 3, 4, 5, 6. Well, what they did is they grouped the first 3 together and the last 3 together. Okay? And out of those first 3 terms, they had a 4x in common. Okay? And they looked at the second group and they found that they all had a 3y in common. And if you look closely, you can kind of see what's left over at 2a plus b plus c. So they factored that out of each one, and then there was 4x plus 3y left over. Okay, so grouping works with 4 terms, but it also works with 6. Okay? Oops. And that's the last one we're going to try here. There's 1, 2, 3, 4, 5, 6 terms. Let's give this a try. Okay, well, let's just group the first 3 and the last 3. And I notice a plus sign in between them, which is good. Okay? Well, let's look at the first group. Do they have a greatest common factor, something that we can take out of each one? And I think the only thing that these 3 terms have in common is an A, if you look at them. So I'm going to take that A out. And I get a 3x plus 2y minus z left over. And on this one, if I look for its greatest common factor, I think there's a b is the only thing that can come out of them. And if I take a b out, I get a 3x plus 2y minus z. And just like we hoped for, is the stuff that's in parentheses the same? Okay, and yes it is, which is good news for us. So what we're going to do is we're going to take those 2 things, and factor it out. We're going to take that away from each one of those. And if you look closely, what's left over? There's just an A plus a B. And that's as far as we can go there. Okay? So lots of different factoring today. Grouping is kind of a review. The only new thing about grouping really is if you see one that has 6 terms in it. Okay, we just do 3 at a time. Okay? But the main thing, the main focus today is the perfect cubes. That's the new one. Okay? And then a little bit with some perfect squares when we have like a to the 4th power and b to the 4th power, how we can separate those into a squared and b squared. Okay? All right, thanks for tuning in.